We now look at complex numbers in terms of quadratic equations. You've done a lot of quadratic equations. Here's an example of a standard quadratic equation, x squared minus 6x plus 5. And you can see that it has roots on the x-axis. It crosses the x-axis twice. This one here, the green one, x squared minus 6x plus 9, is symmetrical and just glances off the x-axis there in one point. The red one, x squared minus 6x plus 12, if you went to try and find the roots of that, you'd find that it doesn't cross the x-axis at all. But actually we can look at it from a complex number point of view. So let's just look at it exactly the same as before, but instead of x, we're going to use z. So find the roots of the quadratic function z squared minus 6z plus 12. It's exactly the same as before. We were used to ax squared plus bx plus c, but now I'm going to use az squared plus bz plus c equals 0. And I'm going to copy them across. Az squared is 1z squared. That gives us a as 1. B turns out to be minus 6. And c turns out to be 12. So I now go into lockdown mode and I start using the numbers from this equation that you're very familiar with, the minus b plus or minus. So here we go. Function z is az squared plus bz plus c, and here's our formula. 1, minus 6, and 12. So here we've got our 1, minus 6, and 12. We're in lockdown mode. We're just using it. And we say, what do we get? The answers were minus b. So minus b would be minus 6, plus or minus b squared, that's minus 6, minus 4 times 1 times c, all over 2 times a. Work it out. Minus by minus is plus. That's 36 minus 48. So 6 plus or minus root 12. 6 plus or minus, now root 12 is a strange one. We can do that. But actually the square root of 12 is actually the square root of 4 times 3, which is the square root of 4 by the square root of 3. And what's the square root of 4? 2 square root 3. So that's where I got 2 square root 3 there. But if there was a minus in there, I just make that 2 square root minus 3. The answer I get is z is equal to 3 plus or minus the square root of 3i. So the roots of that are 3 plus 3i and 3 minus 3i. So I found the roots of the equation, all right. They're not real numbers because they have an I value. If the two roots are that, 3 plus root I, 3i, and 3 minus, what are the factors? Well, when the factors were x equals 4, you said it's x minus 4 is not. So if z1 is equal to 3 plus 3i equals, then how do we, if z is equal to that, z1 minus 3 root I must equal 0. We just take it over to the other side. So that must equal 0, and that must equal 0. So they become the factors. So if they're the roots, they're the factors. Just as we had if x is 4, x minus 4 by taking it over is 4 minus 4, which is not. So now we have two factors. And the factors are that and that. If I were to multiply those two together, z minus 3 minus root I by z minus 3 plus root 3i, what would I get? I should get what I started with, which is z squared minus 6z plus 12, because they're the factors. Is that okay? I could work that out. Z by z is z squared. Z by minus 3 is minus 3z. Z by 3i is 3 root 3i z. Minus 3 times z plus 9 minus 3 root 3i minus root 3i z plus 3 root 3 I, and minus by minus is, that's I by is minus 1, root 3, that's 3. Now if you start looking at that, you can see my z squared is coming through. Am I getting my 6 anywhere? 6z. I've got my 3z and my 3z. That gives me my 6z. This z3i and minus z3i cancel. This and this cancel. And what was the last one? 9 and, what was it, 9 and 3, was it? 9 and 3 gives us 12. So the whole thing comes together. Another way of doing that is to prove it and say, show that the answers of the roots you got are actually factors. Well, what was the equation? The equation was z squared minus 6z plus 12. That's f of z. If this is a factor, we can just plug in the numbers. Like we did with, when x was 2, we'd say, what's f of 2? So when z is this, what's f of that? So anytime we see a z, we put in z. If it's squared, we square it. If it's minus 6 times it, plus 12. If we do all the calculations for that, what do we find? 0 plus 0i. It is a factor. The same for the twin, because it had to be. And this is where I actually multiplied the two factors by each other to prove that I got z squared minus 6z plus 6. So either way, what did we do there? We just started with this, z squared minus 6z plus 12 there, or whatever the case was. That should be 9, that's a 3, is it? That should be 12. Z squared, there's our factors. The first thing we did was we got the roots and we found our solutions. So, you might remember that from before, that the sum of the roots and the product of the roots, if you remember that at all, basically if one of the roots, what were the roots there? The roots were 3 minus 3i, root 3i, and the other one 3 plus root 3i. Z1 was that, Z2 was that. If they are your roots, the other formula they give is that the function is given as z squared. Sum of the roots, add the two of these together, what do you get? 3 and 3, you get 6. Product of the roots, multiply the two together, and you've got to trust me, well, we can multiply it out. What's 3 minus 3i by 3 plus 3i? 3 by 3 is 9. 3 by plus 3 is 3 root 3i. That by that, that's going to cancel. Minus root 3 by 3i. And then root by root is 3. I by I is minus. Plus the other one is plus. 9 plus 3 is 12. As we got before. Give me 1 minute. And finally, just in case it might come up, cubic equations. If you got a cubic equation in complex numbers, here's an example of a cubic equation, and you're told that this is a root. Z1 is 1 plus 3i is a root. Now, if you have a cubic equation on your program, the cubic equation coefficients for the first one, the second one, and the third one, and the fourth will be real numbers. So that's a real number, a real number, a real number, and a real number before the z's. If they're all real numbers, then if you have any complex root, which you have, z1, you must also have its twin. So if z1 is a root, 1 plus 3i, its twin, and what's its twin? Its complex conjugate, 1 minus 3i, must also be a root. So what you can do there is z2 must also be a root. So if one is a root, the other is a root. You can now get the sum of the roots by the product of the roots and say what's the sum of the roots? 1 plus 3i and 1 minus plus 3i. You can find out what the second coefficient is then. And the third one is the product of the roots is plus 10. So what you can find is that z squared minus 2z plus 10 is a solution. You could have done that more slowly. You could have said z1 was given as 1 plus 3i. Therefore, z minus 1 minus 3i is one of the factors. Z minus 1 plus 3i is the other factor. Now we multiply in z by z, z squared. Z by minus 1 minus z. Z by 3i is 3i z. Minus 1 by z is minus z. Minus 1 by 1 is minus with plus 1. Minus by that is minus 3i. Minus 3i by z. Minus or plus 3i. And then minus by 3 by 3 is 9. I by I is minus. That makes it a plus. Adding up all of that and subtracting it all, you'll get your z squared. The z gives you minus 2z. 3iz minus 3iz, they cancel. 3i and I cancel. 1 and 9 gives you 10. So really what I'm saying is that that number there, z squared minus 2z plus 10, z squared minus 2z plus 10, is the other factor. So what you have now is you've got a cubic expression and a quadratic expression, and you're asked to find the last one. So you do that like this. You take the cubic here, you divide into it by the quadratic, and you say how many times does z squared go into z cubed? Z. Z by z squared is z cubed. Z by 2z is minus 2z. Z by 10 is 10z. Take one from the other. You're left with, this is a plus, that's a minus. So you're left with minus z squared plus 2z minus 10. How often does z squared go into minus z squared? Minus 1. You find out that's neat. Naught, naught, naught. The other factor is z minus 1. So if your last factor is z minus 1, then your last root is z equals 1. And what's another complex number called z equals 1 called? 1 plus naught I. So effectively, your answers then for this particular question are, you were told from the outset that one of the roots was 1 plus 3i. Because they were all real coefficients, z2 had to be equal to 1 minus 3i. And when you've done all the sums, z3 happened to be equal to 1 plus naught I. Thank you so much. Don't just jump just yet. Just before, in the second last section on that, just on the notes, on slide number 44, that should be a plus 3 and that should say 12.